Hello and welcome back. In this video, we are going to look at the graphs of the tangent, cotangent, cosecant, and secant functions. Last time we were graphing the sine and the cosine and various transformations of those graphs. So we'll apply a similar approach to the remaining four trigonometric functions and see how their properties differ looking on a linear graph on the xy plane. So let's start with the tangent function. So the first thing I'll keep in mind in terms of the tangent is how it's defined in terms of the sine and the cosine. So if you remember, we have the reciprocal identity for the tangent that's defined as the sine divided by the cosine. So right off the bat, that tells us wherever the cosine is equal to 0, the tangent should be undefined because we'll be dividing by 0. So that means we're going to have some vertical asymptotes. The tangent function will not be continuous like the sine and cosine was, so it's going to affect the domain. So let's consider some points on the unit circle, and I'm going to look in particular at the first and the fourth quadrant. But I'm going to view this as, remember, a clockwise or counterclockwise rotation is a positive angle, and if we were to rotate this way, we would get a negative angle. So I'm going to consider in the fourth quadrant these to be negative angles. And I'm doing that because when we're graphing, we're going to be looking at the origin where these will be positive angles, and then on the left side of the origin, we have to view that as negative. So just to give some context there. And we'll see why this is useful when we get our points together. So let's build a table of values. So we'll have input values and then whatever the associated tangent values are. So we'll call that y. Okay, so you can imagine at 0, this is the point 1 comma 0 because we're on the unit circle of radius 1. And remember, for every point on the unit circle, the x value gives us the cosine and the y value gives us the sine. So to find the tangent, we should just take the y value and divide it by the x value. So for 0, when x equals 0, I'll stick that here in the middle, we should have the point 1, 0. So sine over cosine would be 0 divided by 1, which is 0. We can divide 0 by anything, except possibly 0 itself. So that means on our graph we'll have the point 0, 0. So we'll expect it to go through the origin. Now, what other useful angles for the tangent should we choose, keeping in mind it's sine over cosine? Well, if we think of the angle in the middle, pi over 4, this one's useful for the tangent because the sine and the cosine are the same value, root 2 over 2, root 2 over 2. Hard to plot for the sine or cosine, but the tangent would be root 2 over 2 divided by root 2 over 2, which will just give us a positive 1. So that will be an easy point for us. We can imagine at pi over 4, we'll have the point positive 1. How about up here at pi over 2? This would be the point 0, comma 1. So the sine is 1, the cosine is 0. So we would divide by 0. That tells us at pi over 2, the tangent will be undefined. So that means we should expect to see a vertical asymptote there. So let's go in the negative direction. If we go down here, we can call this negative pi over 4, coterminal with 7 pi over 4. This would be the point, and let me label it. So this will be negative pi over 4. This will be the point positive root 2 over 2, negative root 2 over 2. So notice this time the tangent would be negative 1 because we're taking a negative divided by a positive. But that'll be easy for us to graph. So we can say at negative pi over 4, we should have the point negative 1. Let me make this a little bit nicer. And then down here, we can call this negative pi over 2. This is the coordinate point 0, negative 1. We'll also get an undefined value since we're dividing by 0. So we expect another vertical asymptote here. So this is one sort of cycle through what will be a repeating pattern. If we were to continue, we should see, after undefined, then a negative 1, then 0, then positive 1, undefined, negative 1, 0, positive 1. The cycle will just repeat from there on. So let's plot at least these points on a graph, but we'll imagine that the pattern continues infinitely in both directions. So the standard graph of the tangent, I usually center it at the origin, and we're looking around that area. So I know at negative pi over 2 and at positive pi over 2, we should have vertical asymptotes, and then this would be negative pi over 4 and positive pi over 4, half of that distance. So the first thing I usually do with the tangent is place the vertical asymptotes. We said at negative pi over 2, we should have one here. And at positive pi over 2, we'll have another one here. We have the point at the origin, so at 0, 0. And then the point negative pi over 4, negative 1. So let me place, probably not exactly to scale, but just to place these on here, positive 1, negative 1. So we'll have the point negative pi over 4, negative 1, and positive pi over 4, positive 1. So we'll have a smooth curve in between, and it will approach those asymptotes on either side. So we end up getting a shape that kind of looks like x cubed. That's how I remember the tangent. It has this x cubed like shape, but it is bounded by these asymptotes. So let me add these points in, and I'll throw in some labels. So this is positive pi over 4, positive 1. Here's our central point, 0, 0. And then negative pi over 4, negative 1. So those are the three main points that I keep track of when I'm looking at the tangent function. But it also, again, keep in mind that this pattern continues in both directions. So we would have another copy here, with another pair of asymptotes, and that pattern would continue. If you look at this graph and say like Desmos or a graphing calculator, you'll see that repeating pattern. So this is the standard y equal to the tangent of x. So since it does repeat, we can consider the same idea of the period of this function. And if we think about what this distance is, it's a distance of pi, because there's a pi over 2 distance to the left and a pi over 2 distance to the right. Or we can view it as half of a unit circle. So that's different from the sine and cosine. Those had a period of 2 pi. The tangent's period is half of that, just pi. So let's list the domain range and the period. For the domain, we can take any inputs except for where these vertical asymptotes are. So anywhere except for where the cosine is equal to 0. So we have to think about where that would occur. Well, the cosine is equal to 0 at these 2 points, at pi over 2, down here at 3 pi over 2, but then anything coterminal to those. So that would be 5 pi over 2, 7 pi over 2, 9 pi over 2. Notice these are odd multiples of pi over 2. And we could go in the negative direction as well. So how do we write this? We're trying to say everything except all odd multiples of pi over 2. How can we describe that mathematically? Well, let's come up with an expression for odd multiples of pi over 2. So multiples, we could imagine multiplying this by we want to describe every possible odd number. How can we produce an odd number given any input? Might be a little bit tricky to think about, but the trick is to say something like 2n plus 1. We could also say minus 1 here, too. So think about this. If I were to plug in any integer n and multiply it by 2, I'm going to get some even number. And then if I add 1 to that, that will give me an odd number. You could say minus 1 too, as well, 2n minus 1. Either way will work out. So imagine if I plug in 0 for n, I would get 1. If I plug in 1 for n, I would get 3. If I plug in 2 for n, I would get 5. So notice we're jumping to the odd multiples. And if I plug in negative 1, I would get negative 1, negative 2 would give me negative 3, and so on. So I can say this statement captures all odd multiples, but I need to also define what n is. N is an integer. We don't plug in any like fractions or decimals here. So the way to say that mathematically is I could say n is an element of the set of integers. Can use the set notation symbol. The set of all integers, it's like a z with this double line, kind of like all real numbers has a symbol like this. This is the set of all integers. So let's use this idea and build a statement in set builder notation. So if you recall, we would open up a set. We're describing a set of values. So I'll use curly brackets. So the set of all values x such that, so that's what this line means, such that x is not equal to odd multiples of pi over 2. So I can write my pi over 2 times 2n plus 1. I could also say minus 1. And then I'll define n as being an element of the set of all integers. So that's our way of describing an infinite number of points in concise mathematical notation. So we want to exclude all of those odd multiples of pi over 2. And the integers contain all the negatives as well, so all the negative integers. So that covers everything in both directions. So that will be our domain. How about the range? Well, this goes down to negative infinity up to positive infinity. So our range is all real numbers from negative infinity to positive infinity in interval notation. And then we can describe the period as being a distance of pi. This will repeat itself every distance of pi. So we'll see another copy to the right and to the left. We don't describe like amplitude for tangent functions because amplitude applies specifically for sinusoidal waves, things that are fluctuating around some central axis. So if we did have a number multiplied out front, we would just call that a vertical stretch of this graph. And we could also have a vertical shift up or down. And in our next video, we'll cover horizontal translations. That does have a special name. So basic graph of the tangent, I always think about it being fit between asymptotes. And that's wherever the cosine would be equal to 0. It has a domain everywhere in between those values. And then the range is all real numbers with a period of pi. So I think we get a little summary description for the tangent. Domain is the set of all real numbers except odd multiples of pi over 2. Range is all real numbers. It has odd symmetry. If you imagine it being symmetrical with respect to the origin. It's periodic with period pi. The x-intercepts are multiples of pi. That's thinking about where the sign is equal to 0. So at 0 pi, over here at 1 pi, we would have another intercept. At 2 pi and also at negative pi, another intercept. So that's wherever the sign is equal to 0, the tangent will be equal to 0. And we have vertical asymptotes at those odd multiples of pi over 2. So that's the tangent. Let's imagine the cotangent function. This will be very similar, except the graph will look a little bit different. So let's recall how the cotangent is defined. The cotangent is 1 over the tangent, the reciprocal of the tangent, so we can describe it as the cosine over the sine. So now we should expect asymptotes wherever the sine is equal to 0. So for the cotangent, I'm going to look at the first and second quadrant for our useful points. So everything will be positive angles. And then let's build a similar table of values. We'll call this x, and then we'll make this the cotangent. And let's label some useful points. So at the angle of 0, we have 1, 0. Pi over 2, we have 0, 1. At pi, we have negative 1, 0. And let's use those middle angles too. Since we're still dividing, this time cosine by sine, it'll still be useful. So at pi over 4, this is root 2 over 2, root 2 over 2. And then over here would be 3 pi over 4. So in the second quadrant, the x value is negative. So negative root 2 over 2, positive root 2 over 2. So now we're dividing cosine by sine, so it'll be the x-coordinate divided by the y-coordinate. So notice for 0, we should be undefined. So I would be doing 1 divided by 0. For pi over 4, we should get a value of positive 1. Positive root 2 over 2 divided by positive root 2 over 2. For pi over 2, I have 0 divided by 1, so that will be 0. Then at 3 pi over 4, I'm doing negative root 2 over 2 divided by positive root 2 over 2. Negative divided by a positive will be negative. So we'll get negative 1. And then over there at pi, negative 1 divided by 0, that will be undefined. So this will be one cycle for the cotangent. So let's look at a graph. So now let's look to the right of 0. So let's say this is pi out here. So this would be pi over 2. So we can call this pi over 4. And then this would be 3 pi over 4. So similarly to the tangent, I'll start off first by placing asymptotes. So we should have an asymptote at 0. So that'll be on the y-axis. And then another asymptote at pi. At pi over 2, we have our x-intercept. At pi over 4, it was positive 1. So let's place positive 1 here. And negative 1 would be down here. So positive 1 at pi over 4, and then negative 1 at 3 pi over 4. So we get a similar curve, except it's kind of reflected from the tangent. It starts at positive infinity and then goes down. So it's like a flipped cubic function, but bound also by these asymptotes. So let's label some points. This will be pi over 4, positive 1. Here is pi over 2, 0. And then 3 pi over 4, negative 1. Let me make this a little nicer. So it looks similar to the tangent, except you could imagine it's been like shifted over to the right and then reflected in a way, flipped upside down. The tangent is increasing, whereas the cotangent is decreasing. You can view it that way, from left to right, decreasing. And this will also repeat on both sides infinitely. So we can imagine this pattern repeating to the right and also repeating to the left. Don't think this is official notation, but just to give that idea, the dot 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 meaning this continues, and I put an arrow just showing in that direction. So this is our standard graph for the cotangent. So let's think of its properties. This will also have a restricted domain. So let's say everything except for where our asymptotes live. We can build a similar statement. So it'll be the set of all values x such that x is not equal to what? So we don't want asymptotes wherever, this time wherever the sign is equal to 0. Well, the sign is equal to 0 on the unit circle on this axis. So at 0, pi, 2 pi, then keep going, 3 pi, 4 pi, 5 pi, 6 pi. This time it's just multiples of pi. So this statement will be a little bit easier to describe. We can just say not equal to n times pi, where n is an element of the set of integers. So that will exclude all of those values. All right, and then the range will be from negative infinity to positive infinity, just like the tangent. Goes all the way down to negative infinity and all the way up positive infinity. And the period will also be a distance of pi. It's a bit easier to see here, from 0 to pi. Then we'll have another period off to 2 pi and so on. So that's the distance between the asymptotes. You can view it that way too. So I'll say the period is pi. So standard graph of the cotangent. Also has x-intercepts. Notice it kind of trades properties with the tangent. The cotangent has intercepts wherever our asymptotes were for the tangent, so odd multiples of pi over 2. And the cotangent has asymptotes wherever the intercepts were for the tangent at multiples of pi. So for graphing these two, I usually first think about placing these asymptotes and then getting this like cubic style curve in between. And we can use these easy points. The pi over 4s give us a +1 or -1, so those are easy to place on our graph. All right, let's just sum up a few ideas with the tangent and cotangent, because we can have translations and modifications of these as well. So let's say more generally, we could have some number a times the tangent of something could be multiplied inside and affect the period, so bx and then plus c on the outside, or we could have same thing with the cotangent. So for the tangent, it will have asymptotes where the cosine is equal to 0, since tangent is sine over cosine. And I'm putting the same input here because if the period has been changed, then that will change where the cosine is equal to 0. And for the cotangent, we can say asymptotes where this time the sine is equal to 0. So this number a in front, instead of calling it amplitude for tangent and cotangent, you can just call that a vertical stretch or compression. The period, in order to find it, if we're given an equation like this, the same process is the same as the sine and cosine, except instead of taking 2 pi, we take the original period of pi and divide it by whatever that number is in the equation multiplied by x. So you always start with the basic period. For the sine and cosine, it's 2 pi. For the tangent and cotangent, it's pi. So we can create a similar statement if we flip this around. We could say this number b equals pi divided by the observable period if we were looking at a graph and trying to produce the equation. And then this number c on the outside of the function, that'll be our vertical shift. Either up or down. And if you studied graphing transformations before, you would expect to also see horizontal shifts. We're going to cover that in a separate video for the next section. So we'll leave that out for now. All right, let's see a couple examples of these two. Oops, let me come back here. Oh, maybe I didn't. Yeah, let me erase this really quick. Sorry, I forgot to clear out my slide from my notes. So just clearing that out, and then we'll jump over. There's the first one. Sorry, y'all. And then the second. Make sure the rest is cleared. Okay. So let's look at a couple examples of modified versions of these two. So our first one is y equals 2 times the tangent of x minus 1. So I'll first note what's happening. Our base function is the tangent, and I see that there's been a vertical stretch by a factor of 2. That's what this 2 is going to do. And then the minus 1 on the outside will shift everything down 1 unit. So that will be a vertical shift down 1 unit. All right, so we can try to get this all just in one go, but I usually like to do things as a series of transformations just to try to avoid little errors as we go through. So I'll just do a couple quick sketches first. Let's do a sketch of just the base tangent function. And I'll overview my process again for doing that. So I know my tangent, I'll just look around the origin. And I recall we had asymptotes at pi over 2 and negative pi over 2. So that's usually the first thing I place. That will help orient me where the tangent curve should be. I know it's going to go through the origin, and then it has that cubic kind of movement. And over here at negative pi over 4, we should be down at negative 1. And at positive pi over 4, we should be up there at positive 1. So I'll place a point down here, and a point up here. And then we get cubic style curve, but bounded by the asymptotes. Doesn't look super great, but this is just a sketch to help us modify. Oops. All right, let's introduce the vertical stretch. If I want to do 2 times the tangent of x, I could even just take this graph, and instead of calling that 1 and negative 1, relabel it as 2 and negative 2. So honestly, let's just do that. That will save us this graph. Let's just say this will be 2 times the tangent of x. And instead of 1 and negative 1, I'll just relabel this. Let's say there's a point in between, and this is positive 2, and this is negative 2. A lot of these end up just being relabeling of our axes. So let me label these points. I'll just kind of cram these in here. So this would be pi over 4, positive 2. This would be negative pi over 4, negative 2, and we still have the point 0, 0. So for our actual graph, we just want to take this graph and move everything down 1 unit. So I can imagine subtracting 1 from every y coordinate. So let's produce our real graph here. Y equals 2 times the tangent of x minus 1. Let me actually move this up here so we have a little more room. All right, so I'll still orient us around the origin. Vertical translations don't change the location of our asymptotes, so it should still be here at negative pi over 2 and positive pi over 2. So I'll start there. So vertical asymptote at both of those points. So I should imagine instead of this point down here being at negative pi over 4, negative 2, it's going to shift down 1 more unit. So I need to go down to negative 3. Let's call this negative 3. We'll call that positive 3. So I should have a point at negative pi over 4, negative 3. This is our negative pi over 4 here. This will be positive pi over 4. Our center point should now be at 0, negative 1. And then that other point, pi over 4, 2, should move down to pi over 4, positive 1. So you can see everything just clicks down one little notch here. Then let's build our curve in between. A little bit messy, but there's that cubic kind of curvature bounded by the two vertical asymptotes. And then again, this will repeat. So, you might see questions that ask you to graph 2 cycles of this. You just want to copy and paste the same thing. Going from pi over 2, the next asymptote would be at 3 pi over 2. And then we would have pi over here in the middle. So we'd get another copy of that curve. And we can go in the other direction too. But I'll stick with just graphing one period just to focus on this core behavior. All right, that's our graph. Let's list the domain and range because it wanted us to determine that. So the domain, let's see, has the domain changed at all? Have we shifted anything? Our asymptotes are still in the same positions. So odd multiples of pi over 2. Yeah, because this will be undefined wherever just the cosine of x equals 0. So build statement like before, all values x such that x is not equal to odd multiples of pi over 2. So I can say pi over 2 times 2n plus 1, where n is the element of the set of all integers. And then the range will still be from negative infinity to positive infinity. All right, so just taking our tangent function and applying a couple of graphing transformations. So this time we stretched it by a factor of 2 and moved it down 1 point. Let's add a couple points here. This is 0, negative 1. This would be pi over 4, positive 1. And this is negative pi over 4, negative 3, because we shifted down 1 unit. All right, let's look at one involving the cotangent. So we have y equals 3 times the cotangent of 2x. So what's happening to this graph? I see the 3 out in front. So that is going to cause a vertical stretch by a factor of 3. And then this 2, in terms of graphing transformations, that's a horizontal compression. So that will affect the period, and that will also affect where our asymptotes are. So to find the new period, take the old period, which is pi, and divide it by this number. So it'll be pi over 2. So that will be the distance between our asymptotes. You can think of it that way. You can also think about just multiplying each of our x values by 1/2 or dividing them all by 2. And that will cause that horizontal compression. So let's do this one in a couple steps like last time. Let's remember our first graph. of just the cotangent. So that one, we look going to the right from the origin. We haven't done the horizontal compression yet, so this has a distance of pi. The first asymptote is at pi. Well, we also have one on the y-axis as well, because at 0, the cosine, or the cosine is 1, the sine is 0, so that's 1 divided by 0 for the cotangent, undefined, and then also at pi. It has an intercept at pi over 2, so in between here. Sorry, let me fix my pen. So at pi over 2, we can call this pi over 4 and 3 pi over 4. And then let's recall the cotangent starts at this higher point, so let's call this positive 1, call this negative 1. Let's make it a little more even. So here at pi over 4, cotangent is positive 1. At 3 pi over 4, the cotangent is negative 1. And then at pi over 2, the cotangent is 0. So we get the flipped cubic style curve bound between these asymptotes, which are a distance of pi apart for the cotangent. So this would be pi over 2, 0. This one here is pi over 4, positive 1. And then this one would be 3 pi over 4, negative 1. So similar to the sine and cosine, I'm still splitting up the period into like 4 subdivisions, and then there's some important points in between. And on the boundaries of that, we have asymptotes. So one way of viewing the process of graphing these. So let's apply the vertical stretch. Let's do this in a separate graph this time. So now I want to take the same graph. I want to do 3 times the cotangent of x. So all the y values will be multiplied by 3. So let's do a quick one. So this will still be pi. The asymptotes are still in the same position. So we have pi over 2 in between. This is pi over 4 and 3 pi over 4. And now I need to go up to positive 3 and down to negative 3, because we get that vertical stretch by a factor of 3. So this point should be up here at pi over 4, positive 3. We'll still have this central point at pi over 2, 0. 0 times 3 is still 0. And then at 3 pi over 4, we should be down here at negative 3. This should be a negative here. 2, 3, so down here. So we get a vertical stretch. So let's add some labels. This is pi over 4, positive 3, pi over 2, 0, and 3 pi over 4, negative 3. So we just took all of our y coordinates and multiplied them by positive 3. We could also have reflections. If there was a negative in front of this, then we would see the behavior flip across the x-axis. So still consider that. That can still be a situation. Okay, so at this point, we still have the standard domain of the cotangent. We have to say that n can, or not n, x cannot be equal to multiples of pi. I'll just make a note here. You can say n pi, where n is any integer. That's where all of our asymptotes are. So let's consider now the full graph where the period has changed to pi over 2. Let's say y equals 3 times the cotangent of 2x. This will be our full graph. So we can imagine the period being pi over 2. So this graph, imagine it squishing where the second asymptote appears here and everything happens in between those two asymptotes. Visually on a graph, you can also imagine just multiplying all of these x values by 1/2 or dividing them by 2. So in a sense, we can just really relabel our axis, and that will produce this horizontal compression. If we were, choosing from multiple choice graphs, say on like an online homework or something, I would be looking for that period of pi over 2, where that distance between the asymptotes is a distance of pi over 2 instead of a distance of pi, which we have here. So I'm going to take the approach of really just relabeling the axes, and that will give us the correct values. So I can imagine for each of these x positions, I'm going to divide them all by 2. So instead of at pi, this will be over here at pi over 2. The center point, instead of pi over 2, dividing that by 1/2 will give us pi over 4. Instead of pi over 4, if I imagine taking pi over 4, multiplying by 1/2, that will give us pi over 8. And just think of half of pi over 4. So this will be pi over 8 here. And similarly, if this was 3 pi over 4 originally, and we're dividing by 2, this will be 3 pi over 8. So that gives us our new position. Really, we're now looking from our previous graph at just this interval from 0 to pi over 2. So everything is squished in. And then the rest of the behavior will be the same. This is where our vertical asymptote will be. So at pi over 2 instead of pi. We'll still have one on the origin here. So notice now this will give us our period of pi over 2, this distance of pi over 2 in between asymptotes. So we'll still have a central point in the middle, this time at pi over 4 instead of pi over 2. And then let's say this is positive 3, so that would make negative 3 down here. Let's see if I can just erase that piece. Oops. Can I just get that piece? Yeah, let's make this a little bit possibly nicer. So I should start with a higher point at pi over 8, and then a lower point at 3 pi over 8. And then we get our curve in between. And then let's label these points. So instead of pi over 4, 3, which we had down here, this would be pi over 8, 3. This will be our point pi over 4, 0. And then this will be 3 pi over 8, negative 3. So you can see it as taking our previous graph and then dividing all of our x coordinates by 2. And that causes this compression horizontally. It pushes everything in for this whole cycle to happen between 0 and pi over 2 instead of from 0 to pi. So let's list our domain. Before we said that x could not be equal to multiples of pi. Well, now it should just be multiples of pi over 2. We can do this a little bit analytically by taking our previous statement. We said that x can't equal n times pi. Well, now we have 2x. we're really just saying whatever is inside of the cotangent can't be equal to multiples of pi. So we can make a similar statement and say whatever is inside of the cotangent, in this case it's 2x, this cannot be equal to multiples of pi. And then just solve for x. You can divide the 2 over. So that's doing the same thing, taking our previous value and then dividing it by 2, or multiplying it by 1/2. So x cannot equal now multiples of pi over 2. So let's use that. We'll say our domain will be all values of x such that x is not equal to n pi over 2, multiples of pi over 2, where n is an integer. And then the range, even though this has been modified, the range is still from negative infinity to positive infinity. We can still have all possible outputs. And got a little messy here, but I'll at least box out our modified graph. So it's useful for me. I like to do a series of transformations. You can try to get it all in one once you get a better handle on it. And then, if you're just trying to pick out multiple choice graphs, keep these properties in mind. It's worth thinking, what is the new period? That will tell you where your asymptotes should be. A vertical stretch will tell you where some of these key points will be. Like, oh, this is stretched to +3 and -3. So you can use those to do a little bit of process of elimination if you're looking at a selection of graphs in a multiple choice question. But it's a really good practice to graph these by hand because you get a more kind of intuitive sense for the behavior of these trigonometric functions. It really reminds us that the tangent and cotangent are discontinuous. Um, we have a bunch of asymptotes and then some kind of behavior in between. All right, so that was the tangent and cotangent. But we have two more. Let's consider the cosecant and the secant, and we'll look at these two together. And let's also still relate these to the sine and cosine. Let's recall that the cosecant is equal to 1 over the sine of x. And then also the secant, so let's look at these two and do a little split screen. Let's make a little more room. The secant, let's recall, is 1 over the cosine. So we have similar issues in terms of asymptotes. We can say that the cosecant should be undefined where the sine of x is equal to 0. And the secant we can say is undefined where the cosine is equal to 0. We can say the cosecant will be +1 when the sine of x is +1. Where this is equal to 1. And we can also say it'll be equal to -1 when the sine of x is equal to -1. So it will share those points. When sine has a minimum or maximum, we'll have a point on our cosecant graph. But when the sine is equal to 0, we'll have an asymptote. We can say pretty much the same thing over here for the secant, just in terms of the cosine. It'll equal +1 when the cosine is equal to +1. and it will equal -1 when the cosine is equal to -1. So, and it will be undefined where the cosine is equal to 0. So we get these relationships to the sine and cosine, but what would the rest of the graph look like? Well, the general strategy I suggest for graphing these, and this is what the textbook shows as well, is to first consider the sine and cosine graphs, and then place the cosecant and the secant sort of on top of these graphs. And I'll show you what I mean by that. So let's start with the cosecant, which is related to the sine. So we'll get a quick review on graphing the sine. So I can go out to 2 pi, split it into 4 subsections. So this would be pi, this will be pi over 2, and 3 pi over 2. The sine of x has an amplitude of 1, so we'll go up to 1 down to -1. And the sine function starts at the middle point, sine of 0 is 0, then goes up to a maximum. Sine of pi over 2 is 1, sine of pi is 0, sine of 3 pi over 2 is -1, back to 0 at 2 pi, and then onward from there. So I'm going to just place like a, so these won't be, well, some of these will be points on the cosecant, but some of them will also be asymptotes. So I'm just going to do like a dotted line. So this isn't my cosecant, but this is where the sine would exist. So we get our familiar sinusoidal curve, and it will continue from there. So this is our imaginary sine of x. So we're saying our cosecant graph should have asymptotes wherever the sine of x is equal to 0. So that means at all of these intercepts, we should have vertical asymptotes for our cosecant graph. So I'm going to go ahead and place those. So here at pi, here at 2 pi, also at 0, and this will continue both directions. I can imagine continuing. And then we said when sine equals to +1, the cosecant will equal +1. So they're going to share these points, and similarly for -1. So at the minimum and maximums of where the sine would exist, we'll have a point on our cosecant graph. And then the shape of the cosecant will look like parabolas on top. So on top of the sine graph, and down here it will be like a downward facing parabola. Let me make this a little bit nicer. And so we'll get this point pi over 2 +1, and this point 3 pi over 2 -1. But instead of living like in between those, like how the sine function is, it's on the outside. So it goes upwards and downwards from there, and then it's bounded by these vertical asymptotes. So that creates this parabolic shape. So I wouldn't actually put the blue part on my full graph. That's just sort of a reference. We're referencing the sine, the light blue, I should say. And then the dark blue is our graph of the cosecant. So it has this funny behavior. And then you could imagine copying and pasting this infinitely on both sides. So you get this repeating upward and downward parabola pattern in between asymptotes. So we could say it still has a period of pi in a way. I'm sorry, 2 pi, because it will repeat this general pattern in the same way that the sine function will repeat, because it's constricted by these values of the sine function. So let's list the domain and range. So the domain is all values except where the sine is equal to 0. So we want to exclude these multiples of pi. So at pi, 2 pi, and so on. 0 pi, 3 pi. negative 2 pi. So all values x except multiples of pi. This is where n is an integer. And then how about the range? So it goes down to negative infinity up until negative 1 and stops there, and then picks back up at positive 1 and then goes off to positive infinity. So we want to describe those two disconnected intervals. So I could say from negative infinity to positive 1, and then join that with the second interval from 1 to positive infinity. So negative infinity to negative 1. Let me fix this. Negative infinity to negative 1 union 1 to infinity. So this interval joined with this interval. So again, the process for the cosecant is to first imagine the graph of the sine. Place asymptotes wherever that graph is equal to 0, so where it crosses the x-axis, and then place these parabola shapes at the maximum and minimum points on the sine function. And that will give you the graph of the cosecant. So let's do a similar thing for the secant, which will be on top and below the cosine function. So I'm going to start by graphing like the ghost of the cosine and then placing the secant on top and below, and then our asymptotes accordingly. So cosine goes out to 2 pi. Let's split this into 4 pieces. So this would be pi, pi over 2, and 3 pi over 2. And I'll call this positive 1 and negative 1. The cosine starts at its maximum. Cosine of 0 is 1. Then down to the middle point, pi over 2 is 0. Cosine of pi is negative 1. Cosine of 3 pi over 2 is 0. And the cosine of 2 pi is back at positive 1. And I'll do a little imaginary cosine curve here. So in a similar way to the cosecant, we said the secant is undefined wherever the cosine is equal to 0. So that means here at 2 pi, we'll get a vertical asymptote. Also at 3 pi over 2, vertical asymptote. We can continue that pattern in both directions. And then it will have parabolas at these maximum and minimum points. So at 0, we'll have the point here going upward. We'll have another asymptote if we continue that way at negative pi over 2. Then a downward facing parabola shape here at pi, bounded by these asymptotes. And then another upward one over here. And then this pattern would continue in both directions. So let's stick a few coordinate points on here. This would be pi comma negative 1. We have 2 pi at positive 1. Also over here, 0, positive 1. Have to stick it in here. It's that point. So it's kind of like a shifted version of the cosecant graph. So let's list its attributes. So this is the secant of x. So the domain, what do we want to exclude? Set of all values x such that x is not equal to what? Pi over 2, 3 pi over 2. Next one would be 5 pi over 2. And so odd multiples of pi over 2. That's what we want to exclude from our graph. So we built a similar statement when we were discussing the tangent. Because notice they're related in that way. Tangent is sine over cosine. Secant is 1 over cosine. So they both have asymptotes wherever the cosine is equal to 0. So you can relate them in that way. So all values x such that x is not equal to odd multiples of pi over 2. I can say pi over 2 times 2n plus 1, where n is an element of the set of integers. And then the range, it'll be the same as the cosecant. So from negative infinity to negative 1, we can join that with the interval from positive 1 to positive infinity. So to graph the cosecant and the secant, imagine their respective reciprocal partner. So the sine for the cosecant or the cosine for the secant. So imagine the graph and then place the cosecant and secant graphs like on top and below those, using these maximum and minimum points. And this applies to transformations as well. So if the cosecant has been transformed in some way, we can imagine the same transformation to the sine function and then follow a similar process. So let's see an example of that. So this gives us y equals 2 times the cosecant of x minus 1. So here's our strategy. I'm going to use the related graph of the sine, because cosecant is 1 over the sine. So I'm going to use the graph of y equals 2 times the sine of x minus 1. And let's see what that graph looks like, and then place the cosecant on top and below that graph. So first I will imagine, I'll do like 2 steps. Let's do 2 times the sine of x. It's easy to get that in one graph. You can imagine the sine wave, but it now has an amplitude of 2. So this would be positive 2, negative 2. It'll go out to 2 pi. So be pi in between, pi over 2, 3 pi over 2. Sine starts in the middle, goes to its maximum, down to the middle point, down to the minimum, back up to the middle. Okay, and then this needs to be shifted down 1 unit. You have a vertical shift down. So let's imagine this will be now 2 sine of x minus 1. So I can imagine the central axis has been shifted down 1 unit. Let's make this a little bit bigger. So instead of on the x-axis, I can imagine that central axis is down here at negative 1. It can be helpful to visualize that this isn't an asymptote, but it's the sinusoidal axis. So our amplitude is still 2, so we should go up 2 spaces above that axis, now to positive 1, and 2 spaces below, now at negative 3. It'll still go out to 2 pi, with pi in between, pi over 2, 3 pi over 2. And then let's use that same sine wave pattern. So starting at the middle point, which is now down here at negative 1, then up to the maximum, so up here, back down to the middle point, down to the minimum, and then back up to the middle point. So let me label a couple of these. This would be at pi over 2, comma 1, and this is at 3 pi over 2, negative 3, because we have that amplitude of 2 spots above and below that central axis. And then this would be, just for good measure, 2 pi negative 1 instead of 2 pi 0. All right, but that's not our graph. We want the cosecant. So let's imagine this graph, but then place the cosecant above and below. So let's get our actual graph over here. We'll say this is positive 1. You want to go down to negative 3. So let's place our sine wave. So just imagining, and let's also bring this out to 2 pi. So we would have pi in between that. This would be pi over 2. So that would make this 3 pi over 2. So middle point, maximum point, which will be shared with the cosecant, back down to middle point at pi, down to the minimum at 3 pi over 2, back up to the middle point. My scaling is a little bit off, I think. Let me raise this point a little bit higher. But we just want a rough idea of where the sine function is. I'll just imagine that if I was using like pencil, I would go back and erase it later. So we should have asymptotes in these middle points. So wherever that middle part of the sine wave is, that's where our asymptotes will be. And then we'll share this maximum and minimum point with the sine graph, and then go up in this bounded parabolic style curve above and below. So let's label these points. This will be pi over 2, positive 1, and then this would be 3 pi over 2, negative 3. So this will be our graph of y equals 2 times the cosecant of x minus 1. Now let's give the domain and range. So we will exclude all multiples of pi, because that's where all of our asymptotes are. So all values x such that x is not equal to, just say, n pi, where n is an element of the set of all integers. And then the range. So this has been shifted vertically, so it will affect the range. We want everything below negative 3 and above positive 1. So I can say everything from negative infinity until negative 3. Oh, and let's include this. We want to include negative 3. Yeah, these will be included. And we'll join this from positive 1 to positive infinity. Yeah, I might have forgotten to include them on our previous statements. Let's go back and see. So here, yeah, let's include these endpoints. So we want to include -1 here, include +1, because it is defined at those points. Yeah. So include it here and include it here. All right, and that wouldn't affect the tangent and cotangent since it's going to positive and negative infinity. So yeah, quick correction here. When we're giving the range of these, we'd include these endpoints since it is defined there. So from negative infinity to -3, including -3, and then from +1 off to positive infinity, including +1. So we'll update on the range there. So again, the process is to, for the secant and cosecant, imagine the graph of their corresponding reciprocal partner. We were looking at the cosecant here, so I imagine the graph of the sine function. And then place asymptotes on those middle points. This got shifted, so it's no longer exactly where it's crossing the x-axis, but this is that central axis for the sine. That's where your asymptotes will be. And then the cosecant joins with the sine function at these maximum and minimum points, and then goes up to infinity and down to negative infinity. And there's a similar result with the secant graph, comparing it to the cosine. So a little bit tricky, but with a bit of practice, should feel a little bit better. Just remember to relate these to either the sine or cosine function, whatever their reciprocal partner is. All right, and then if you want to go back in your notes and update these boundary points and to include these boundaries. Okay, so that's it for this section. So we covered the graph of the tangent function and the cotangent function and transformations of those two. And then we looked at the graph of the cosecant and the secant and also associated transformations. So next time we'll look at horizontal transformations, which we will describe as a phase shift. So we'll go into that in our next video. All right, that's it for this one, and I'll see you next time.